morning, guys. So today we're going to start chapter 7, which is on sequences and series. And we're going to start out with the first section, 7.1, defining and using sequences and series. So our goal or objective for this lesson is to be able to define what the sequences and series are and also be able to use them. And before we get started, I'm just going to open up my calculator because we may need that. So hopefully that will start to load here while we get started. Okay, so a sequence is a function whose domain is the set of consecutive integers. So the inputs that you would be putting into that function, whatever number you're starting with, you go from there. So 1, 2, 3, 4, and so on, or 5, 6, 7, 8, and so on. Or it could even be negatives. The range then would give the terms of the sequence. So we start out and we're saying, okay, what is the first number? We plug in number 1. What is your answer? You plug in number 2. What is your answer? Plug in 3. What is your answer? And those answers create some sort of a pattern or sequence. There's two types of sequences. There is infinite sequence, which is basically just like what it sounds like. It goes on for infinity. So you'll notice that little ... there at the end indicating that it's an infinite sequence. And there's also finite sequences, which are just for determined, like a predetermined set of numbers. So maybe we only want to know 6 terms. So like if we're applying this to a real life scenario, for example, and we were talking about maybe rows of chairs or something in an auditorium, obviously they're not going to go on for infinity. So maybe they add 2 chairs onto each row as they build the rows, but it's only going to go on for a certain period or a certain amount of rows or something like that. So that would be an example of a finite sequence. But when we're talking about maybe like things with money or investments or those kinds of things that can theoretically go on for infinity and keep increasing or things like that, that would be an infinite sequence. So the first thing we're going to talk about is just writing the terms of sequences. So basically, for me, it helps me a lot when I just sort of put everything into like an input-output table kind of setup. That sort of helps me, hang on one second. That sort of kind of helps me like keep it organized so I remember exactly what am I doing and that sort of thing. So let's see if I can pull this up here on the side. Okay, so if I were to write the first 6 terms of this sequence here, this is the formula that we're using. So the first 6 terms tells me that I have to plug in basically for my inputs the numbers 1 through 6. That's essentially what that means. So if it helps to kind of keep it organized by making it like an input-output table setup, that might be something that you want to do. Otherwise, you can just kind of list them. So I'm going to show you how to do it this way, and then I'll just show you how you could list the answer. So if I'm plugging in these numbers, obviously I'm going to put in the n, right? That is my input or my domain. So I'm starting with 1 because it's the first 6 terms. 2 times 1 is 2. 2 plus 5 is 7. So my first number in my sequence is 7. So my answer would be something like this. If I want the first 6 terms, I'm just going to list them. Okay, then I would plug in a 2. 2 times 2 is 4. 4 plus 5 is 9. So the second term in my sequence is a 9. Then I would plug in the 3. 2 times 3 is 6. 6 plus 5 is 11. So the third term in my sequence is 11. Then I would plug in a 4. 2 times 4 is 8. 8 plus 5 is 13. So the fourth term in my sequence is 13. And then we could probably figure out the pattern by now that they're increasing by 2 each time. And then you could figure out that the next 2 numbers in the sequence are 15 and 17. So we're just going to practice first writing the first 6 terms of each sequence. Now, another option you have here is you could always use your graphing calculator. So, oh no, something's going on with this. All right, well, I don't know why that was happening, but anyway, so write the first 6 terms of each sequence. So again, because I have this first 6 terms, I'm just going to kind of set it up as that input-output table. So I know I'm plugging in 1, 2, 3, 4, 5, and 6 for each one of these, and then I'm getting my outputs, right? So for number 1, if I plug in the numbers, each of these I'm just adding 4 to. So 1 plus 4 is 5, 2 plus 4 is 6, 3 plus 4 is 7, 4 plus 4 is 8, 5 plus 4 is 9, 6 plus 4 is 10. So my answer here would just be 5, 6, 7, 8, 9, and 10. So that would be the first 6 terms of that sequence. So now if I'm moving on to number 2, this time they're setting it up as an f of n in a function format instead of the a sub n format, but you're not going to do anything differently. It's just a different way of kind of setting it up. So this time we have a different type here. Instead of it being linear, it's got an exponent, so it's an exponential. So when I go to plug in this one, remember your order of operations with PEMDAS, you have to do that exponent portion first before you do the rest. So if I were to put in a 1 here, 1 minus 1 is 0, and anything raised to the 0 is 1. Then if I put in a 2 here, 2 minus 1 is 1, and negative 2 to the first power is negative 2. If we put a 3 in there, 3 minus 1 is 2, and negative 2 to the second power is positive 4. If we put in a 4, 4 minus 1 is 3, negative 2 cubed is negative 8. 5 minus 1 is 4, negative 2 to the fourth power is positive 16. And then negative 2 to the fifth power would be negative 32. So our answer here, the first 6 terms of the sequence would be 1, negative 2, 4, negative 8, 16, and negative 32. Now, what I was going to tell you with the calculator is that if you went into your graphing portion of the calculator, into your y equals menu, and you typed in like y equals n plus 4, or for this problem, y equals, and then you did the negative 2 raised to the n minus 1, and then you went to your table of values, you could just get the numbers right off of your table. So that's another option, especially when you get to like a multiple choice question or something like that, if you don't want to keep plugging the numbers in over and over again. Okay, so let's take a look at the next two. So when you have a fraction, okay, so this one's a little bit different. It's probably going to be easier to actually do it without the calculator. I mean, you could, but so now you have the n on the top, so you're kind of putting in all of these numbers in that end. So each one of these answers will be some kind of fraction, but the numerator is going to be whatever your input value is. Now the denominators are going to be that input value plus 1. So 1 over 2. Then when I put in the 2, I get 2 over 3. When I put in the 3, I get 3 over 4. When I put in the 5, I get 4/5. 5, 6, and 6/7. So your answer for this one, the first 6 terms of this sequence would be 1/2, 2/3, 3/4, 4/5, 5, 6, and 6/7. And that's what that would look like. Okay, so number 4, another exponential one. So again, if you want to do the table to keep it organized, you can. You can do it by hand. You can look up the table on the graphing calculator, whichever way works for you. So 2 to the first power is just 2, and 2 minus 3 is negative 1. 2 to the second power is 4. 4 minus 3 is positive 1. 2 to the third power is 8. 8 minus 3 is 5. 2 to the fourth power is 16. 16 minus 3 is 13. 2 to the fifth power is 32. Minus 3 is 29. 2 to the sixth power is 64. Minus 3 is 61. So our first 6 terms of the sequence would be negative 1, positive 1, 5, 13, 29, and 61. All right, so we've got 2 more. They are both, one's linear and one is exponential. So for these, I would definitely encourage you to try them on your own, pause the video, and then just check your answers maybe after that. Okay, so for this first one here, again, we're just plugging in those first 6 terms. When you plug in 1, you get 5 minus 1, which is 4. When you plug in the 2, you get 10 minus 1, which is 9. You plug in the 3. 5 times 3 is 15. 15 minus 1 is 14. Then you have 19, 24, and 29. So those first 6 terms, 4, 9, 14, 19, 24, and 29 are the first 6 terms of that sequence. And then this last one here, 2, 3, 4, 5. Okay, so this one again, exponential. So plugging in the 1 gives us a power of 0, which makes everything equal 1. Plug in the 2, we get negative 3 to the first power, which is negative 3. Plug in the 3, you get negative 3 to the second power, which is positive 9. When you plug in the 4, negative 3 to the third power, which is negative 27. Plug in the 5, negative 3 to the fourth power is 81. And then when you plug in the 6, negative 3 to the fifth power is negative 243. So your first 6 terms are 1, negative 3, positive 9, negative 27, positive 81, and negative 243. All right, so basically that is how you can come up with terms in your sequence. So if you are given the rule for the sequence, you can just input the numbers in consecutive order and you can come up with the actual numbers in the pattern or sequence. So now if we were to do the opposite of that, so I was giving you the rules, which are like the formulas or the functions, and you would maybe just get the sequence and need to come up with that rule. So what's the general rule of the infinite sequence 2, 4, 6, 8? So when we're dealing with a linear sequence, and I'll show you how you would know that, it's a little bit easier. When you're dealing with exponential sequences, sometimes there's a little bit of guessing and checking involved for some of them. Tomorrow, the next 2 lessons after this, the next 2 days, will specifically go over arithmetic and geometric sequences, and then there's a specific formula you can use, which is a little bit easier than guessing and checking. Okay, so what is the general rule of the infinite sequence 2, 4, 6, 8, and so on? So because they're basically giving you the outputs here, we know the inputs would be 1, 2, 3, and 4. So usually what I do is I kind of put them into an input-output table. Since they're giving me the outputs, I know the inputs would have to start, in order. If they're giving me the first 4 terms, it's 1, 2, 3, 4 for my inputs. And then I want to kind of figure out, well, if you remember what we just did on the last page, all these inputs were just plugged into an equation and then we got our output, right? So if I plug in a 1, I need to get a 2. Or if I input that 2, I need to get a 4. If I input a 3, I need to get a 6, and so on. But you might have noticed, like if we went to the previous page, there might have been some kind of pattern with the numbers. So all the linear equations, which are over here on the left, notice that the patterns, like the numbers that you ended up with as your sequence, they were increasing by the same thing continuously. So if you look at number 1, go 5, 6, 7, 8, they were all increasing by 1 to get to the next number. And number 3, the top numbers were increasing by 1, and the bottom numbers were also increasing by 1. So again, it's an addition, like each number is increasing or adding something each time. Then the next one in number 5, to get from 4 to 9, we're adding 5, adding 5, adding 5, adding 5, adding 5. So again, it's an addition type of thing happening. It could also work if it was decreasing. Sometimes the patterns are decreasing, and that's more like a subtraction if you're thinking of it that way. Now, if you look at the 2 patterns on the right-hand side, numbers 2, 4, and 6, those were exponential patterns, and those are definitely, like if you look at number 2, 1 times 2 is 2, 2 times 2 is 4, and of course there's a negative involved because they're switching signs. Then the next pattern, you went from negative 1 to positive 1, but then you jumped to a 5, and then you jumped to a 13, so it was increasing those, it wasn't adding the same thing each time. There's definitely something being multiplied somewhere in there. And then number 6, also here, you're being multiplied by 3 each time, but it's a multiple, not an addition. So with that being said, when you look at your pattern and you can see that there's something being added each time, like this, you know it's going to be linear. Okay, so when you know it's going to be linear, think about y equals mx plus b, right? So instead of y equals, we do a sub n equals, and then instead of the x we're using the n, right? So we're, instead of using an x and a y, right, we're using n and a sub n, but it's the same kind of idea. So instead of y equals mx plus b when you're doing linear, it's a sub n equals something n, and then, so let's say mn plus b, kind of like that. So for this one, this number that's increasing each time, that's kind of like your slope. So it's going to be 2n. And then, are you adding or subtracting anything? Well, that's where you kind of have to test it out. So if I plug a 1 in here, 2 times 1, I get 2. If I plug in a 2, 2 times 2, I get 4. If I plug in a 3, 2 times 3, I get 6. So I don't have to worry about adding or subtracting anything. It would really be like plus 0. So our rule here is a sub n equals 2n. So all we got to do is take our input, multiply it by 2, we get our output. That's it. So a sub n represents the the nth term of the sequence. So what if I wanted to know the 8th term? So I have the 1st, 2nd, 3rd, and 4th. But what if I want to know the 8th term, a sub 8, right? So 2, 4, 6, 8, we know this is 10, 12, 14, 16, right? I can figure out that it's 16. Okay, that's not too bad, but then what if I want to know the 31st term? That's going to take me a much bigger chart, or I'm going to have to count by 2s much farther to get to that answer, right? Now, of course, you might be able to do that. It's okay. You can do it that way. But if I said a to the 243rd, you're not going to want to count by 2s that far. So that's where it's really important to be able to write this rule that we have right here. Because now, once we have this rule here, we can use that for any number of terms. So if I did, for example, even though we just figured out the a sub 8 using the chart, if I just did 2 times 8, what do I get? 16. That's a lot easier than going 2, 4, 6, 8, whatever. Now, if I want to know a to the 31st, all I have to do is 2 times 31. That will tell me my 31st term in the sequence, which of course is then 62. So any term you want in the sequence, if you have the rule, you can just plug it in. Like, oh, I want to know what is the 10th number in the sequence. Plug it in, and then you'll find out what is that 10th number. If you want to know the 100th number, the 1000th, or whatever it is. Okay, so let's do a couple examples here. Describe the pattern and write the next term of each sequence. So again, they're giving you the outputs. So what I like to do, and you don't have to do this, it's just, to me, it makes it a little bit easier to kind of figure out what's happening. I'm given my first 4 outputs for the sequence. So basically my n values are still starting with 1. 1, 2, 3, 4, and then my a sub n's are 3, 5, 7, and 9. Those are the numbers in my sequence. Now, before I write my rule, I'm going to well, what is that pattern here? It's kind of going to be your slope if it's linear. So we have 3 to 5 to 7 to 9. So we're adding 2 each time. So when you go to write your rule, then we know it's linear. So a sub n equals 2n, and then you have to figure out, are you plussing or subtracting anything? And that's how you just check it then. So let's say we want to check the first term. If I plug in a 1 here, right, 2 times 1 is 2, but I need my output to get a 3. So what else do I need to add to that? A 1. So now let's check it for this next one and make sure it works for that too. So if I plug in a 2, 2 times 2 is 4, plus 1 is 5. So it works for that one. What if I plug in a 3? 2 times 3 is 6, plus 1 is 7. So it looks like it's working. 2 times 4 is 8. 8 plus 1 is 9. So our rule here is 2n plus 1. Now it says write the next term of each sequence. Well, at this point, we know the next term would be 11. If we had to continue it even further, we would know it'd be 13. They're just going by 2s. Okay, so now let's take a look at number 2. So again, number 2, they're giving us 4 outputs here. So we have -4, -8, -12, and -16. And how do I get from each of those numbers? -4 minus 4 is negative 8. Negative 8 minus 4 is negative 12. Negative 12 minus 4 is negative 16. So if I'm writing my rule, how do I get these a sub n's? What do I have to do to my n value? Well, we know it's going to have to be multiplied by a negative 4. And then is anything going to be added or subtracted there? So if I take this 1 and I multiply it by negative 4, I get negative 4. So far that looks good, right? Let's check it for the next one. What about a 2? Negative 4 times 2, that's negative 8. 3, negative 4 times 3, that's negative 12, and so on. So for this one, that's all I have to do for my rule. I don't have to add or subtract anything to it to make it work. So now the next term in the sequence, all I'd have to do is 5 times negative 4, and I would get my negative 20, or you could have just carried out the pattern another negative 4 and gotten it that way. Okay, so let's take a look at number 3. So again, they're giving us the first 4 in the sequence. So we have negative 1, negative 8, negative 27, and negative 64. So let's see if we can figure out a pattern here first. So if I go from negative 1 to negative 8, I am actually subtracting 7. But then when I go to negative 8 to negative 27, I'm not subtracting 7. So that's not going to work. We can't use the same thing that we were doing before. So now we have to say, okay, well, what kind of pattern is going on here? So we know it's not adding or subtracting something over and over again, but maybe it's some kind of a multiple or something like that. So I could multiply my negative 1 by 8. But then if I do 8 times 8, I'm not going to get 27. So that's not too helpful. So then you might need to kind of look at the inputs and see if there's anything happening to the input to get each output. So maybe each input was cubed or squared or multiplied by a number or something like that. So this is where there's guessing and checking kind of coming in. And you're just going to have to kind of play around with it. There's not really necessarily an easy way to do it. So usually what I do is I try not to start with the ones because there's so many things you can do to a 1 and get a 1. Like you can multiply it by itself. You can raise it to itself and you're still going to get the same answer. So it's not so helpful. So usually I try to look at the second or the third number in the sequence and think, is there any relationship between those numbers there? So like what can you do to a 2 to get an 8? What can you do to a 3 to get to 27, right? So to me, and also you could look at the 4 and the 64, I'm noticing that these are all perfect cubes. So if I take my n value and I cube it, okay, so if I take 2 and I cube it, I get 8. If I take 3 and I cube it, I get 27. If I take 4 and I cube it, I get 64. Now the only trick is that these are all negative. So after I cube it, I'm going to have to multiply it to a negative 1. So this would be my rule. So again, this one's a little bit trickier. Now 5, the perfect cube there would be 125, so that's negative 125. So some of them are going to take a little bit of playing around with. Okay, so let's take a look at number 4 now. So my n values are 1, 2, 3, 4, and they're actually giving us the 5th term as well here. And we have 0, 2, 6, 12, and 20. All right, so for this one, obviously adding 2, adding 4, adding 6. So we see that we're adding, but the number's changing each time. So there's still a pattern there, but it's not going to be a linear pattern. When the number that you're adding by is increasing, there's going to be some kind of exponent or multiplication involved there. So again, at this point, if you notice that the number is going like up by 2, then up by 4, then up by 6, up by 8, then you're probably going to have something being squared. And again, you might want to look at those n values and see how can I get to those outputs. So let's start out with just squaring. When you're adding, different numbers here and they're all increasing, like the number you're adding by is increasing by a constant amount, that's usually a clue if there's going to be something squared. So if I take the number squared. If I do 2 squared, I get 4, right? If I do 3 squared, I get 9. If I do 4 squared, I get 16. And that's not giving me these answers I need down here. So let's play around with it and see if there's something we can do that'll work. So if I do 2 squared, I get 4. How do I get back to a 4? What would I do? Well, 2 squared is 4. And if I subtract 2, I would get that answer that I have there, right? So let's try for the next one. 3 squared is 9, but minus 2 would only get me to 7, and I need a 6. So I know this minus 2 is not the answer, but what else could work? I mean, minus 2 worked the last time, but this time I want a minus a 3. So let's take a look at the next one, see if that kind of gives us a clue. If I do 4 squared, I get 16. What would I have to subtract to get to 12? A 4. So you're noticing each time you're subtracting by the original number, which was the n. So your rule this time would be you take the n and you square it, and then you subtract the n from that product. All right, so that was a little tricky. When we take the quiz, for the most part, the ones you'll be able to use the formulas you're going to learn over the next 2 days. Don't panic about that. Plus, you have multiple choice. So when you have multiple choice, you can work backwards and check your answers. So no worries there. Okay, so let's do this with a word problem. So solve a multi-step problem. At a grocery store, there's a display of apples in the shape of a square pyramid with 7 layers. So you probably noticed this, like, I don't know if you watched Curious George when you were little, or those kind of shows where they have a big square, like, display at the grocery store. And then, like, you know, there's a whole bunch of apples and they, like, pyramid them up on top of each other. So I'm just going to kind of do, like, a side view. Obviously, I can't draw the whole thing, but if you're looking at the side, there's your one on the top, and then how many apples do you have underneath that one on the top? So layer 1, we'll work our way from the top, has 1 apple. How many apples do you have underneath that one holding it up? Or oranges or whatever? You would have 4, right? And then you'd place that top one kind of like in that middle section. So on the second layer, you have 4 apples. On the third layer, how many do you have to hold those 4? Anybody know? You would actually have 9. So see if you can figure out the pattern here, what's happening. So notice this is 2 by 2. This is 3 by 3. So what do you expect the next one to be? That's right. It's going to be a 4 by 4. So it'd be something like that. And then that would be a total of what? 16. So now you might notice that by this point, 1 squared is 1, 2 squared is 4, because you're multiplying the length and the width, basically. It's an array. So 5 times 5 would be 25, 6 times 6 would be 36, 7 times 7 would be 49. So let's see if we can come up with that rule. So if we take a look at this, these are the n values here, and these are the a sub n, right? So what am I doing my n values to get those a sub n's? We're squaring them, right? We're taking that n value and we're squaring it. And that's it. We don't have to add anything to it or whatnot. So that would be our rule. Now, when it says to graph, well, we already have our input-output table here, and you can also do this on your graphing calculator. So if I have 0, 1, 2, 3, 4, 5, 6, 7. This is an exponential graph, so I'm just going to go by like 10s maybe. Actually, I'll go by 5s. Hold on. So 5, 10, 15, 20, 25, 30, 35. Get the idea. Okay, so we have 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, 6, 36, and then if you had room, the last one would be up there somewhere. So it's an exponential curve. All right, so that's pretty much all the information about sequences. So now on the last part of the notes, we're going to go over a series. So there's something called a series, which is basically when the terms of the sequence are added together and the resulting expression is a series. So let's say that apple problem we were just talking about, if there's 7 layers, right? Now this obviously can really only happen if it's finite. And I want to know, well, how many apples are in that entire display? So we know we have 1 on the first level, then 4, 9, 16, 25, and so on. If we add up all these numbers, what's the total amount of apples that we have in the entire display? So that's what a series is. So a series is when you want to find out what all the numbers in your sequence add up to. Again, there's 2 types. There's the infinite series, which obviously is more theoretical because you can't actually add it up to infinity, but it'll tell you, about where you'll get. And then you have your finite series, which would be similar to the apple example that we just did, where you have the 7 layers, and then you want to add up all the apples in each layer and find out how many total apples you have in the display. So there's something called summation notation or sigma notation to write a series. And I'm going to try my calculator one more time, see if I can get it to load for a second, because there's definitely stuff on there that will be helpful for you. If not, I will have to just kind of verbally walk through it and email tech support tomorrow to try to see if I can get that sorted out. So I'm just going to give it 1 second. Doesn't want to cooperate. All right, so no calculator for today, unfortunately. Okay, so here it says you can use summation notation, which is called sigma notation. So you've probably seen this little Greek letter called sigma. You may have seen it at college or something with a fraternity or something like that. But it does actually mean sum. If you ever use Microsoft Excel or Google Sheets, you'll see the sigma used for sum. So whenever you want to sum up a column of data or a row of data in a spreadsheet, that little button up at the top, usually in the browsing strip across the top, will be how you would add up a column. You'd highlight the column or the row of data that you want to add up, and then you click on that little sigma button, and that's what it does. So it's used frequently in spreadsheets and stuff like that for, inventories and that sort of thing. So basically, if you were going to use it to represent a series, again, we're talking about sums, right? So if you're saying, okay, I want to sum up this information, basically what you would do is you would have the starting number on the bottom here. So where am I starting? The top is where am I ending? So like, for example, if we're doing the apple problem, we would start at the first level and we would end at the 7th level because there was seven layers or levels of apples, right? So we're going from 1 to 7. That just tells the calculator, the computer, whatever, how many levels are we going or how many steps are we going? And then over here on the right is going to be that rule. So when we did the apple problem, we had n squared. So that's what would go over here on the right. Now, they're using the variable I here to represent the index of summation because it's called an index. Obviously, the number on the bottom, that's your lower limit or your first input. And then the top number is your upper limit or your last input. Sometimes you'll see it with other variables instead of an I. They'll just use the n or an x or k or whatever. But they're all talking about the index. That's what that means. What are you going from? What's your first input? What's your last input? And then the summation, the whole sigma basically means sum. So that's what it's doing. So it's telling you I'm going to find the sum of all the numbers in the sequence from step 1 to step 4 of, in this case, 2i. That's the rule or the formula. If we were doing the apple problem, it would be n squared. So it just depends what you're doing. Now, if you have an infinite series, obviously you don't have an ending number. So if you want to find the sum of it infinitely, you'd have to put that little infinity sign up at the top. That's how you would write it out. Okay, so write the series using summation notation. So all we're doing is writing it out. We're not calculating anything. So the first thing we would do is we would write our sigma, which is this like very funny looking E, right? And this is where my input output table kind of comes in handy. So 1, 2, 3, right? This is 1, this is 2, this is 3. But this one, they're not telling us how many numbers are in here. So I'm going to kind of figure this out, right? So if my pattern's going up by 4s, 12 plus 4 would be 16. 16 plus 4 would be 20, and then 24. So that's 4, 5, and 6. So this was a little tricky because you actually are going to do it for 6 numbers, but they only wrote 4 of them down there because they were getting lazy. So they're like, oh, we'll put a dot, dot, dot in the middle, and you have to figure those out. So now we know that our index is starting at the first term, which is 1, and we're going to go up 6 terms. So the top, you just write the 6. So we're going from 1 to 6. And now we need to figure out, well, what is that rule, right? So we were doing our rule. This is linear because it's plussing 4 each time. So we're going to start out with 4n, just like we did on the other page. We got to figure out, well, what is that formula or rule? So if I plug in a 4, 4 times 1 is 4, 2 times 4 is 8, 3 times 4. And so our rule is very simple here. It's just 4n. So that 4n or 4i is going to go on the side. Now, it doesn't matter if you use an n or an I, just stay consistent. So if I use a 4i here, this is going to say I equals 1. If I did 4n, then it would say n equals 1. Just stay consistent, whatever variable you choose. And of course, the top doesn't need a variable. It's just, whatever input you went up to. So now we do number 2. At least this one, they gave us 5 numbers, and we don't have to fill in any missing ones. So I'm just going to make this into an input-output table to kind of make it a little easier for me. So when we do our sigma this time, we know that our index is starting at the input of 1, and we're going up to 5. And now we need to do our little rule over here on the side, so I'm going to figure that out. So my pattern here this time is not going to be linear because I'm going up by 3, then up by 5, then up by, 7, and so on. So let's start out with a squared and see if that helps us. So 1 squared is 1, it works there. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, so it's good. So then that's going to be my little rule over here on the side, and that's what my summation notation will look like for that problem. All right, so now we're just going to do the opposite, find the sum of each series. So this one here, you would just have to make an input-output table and then add them up. There is, the newer calculators do have a sigma notation button on their calculator, but I think it's only on like the really new ones. Like if you have one of those color ones that you have to plug in to charge and stuff, it's on those. It's not on the ones I loan out. Those are too old, those models. And I'm not sure about the 84s. I'd have to double check on there. Now this time the input's a little different. We're starting at 0. So you're actually going to have to start out by plugging in 0 and then going all the way up to that 5. And you're plugging them into 12 times I. So you're just multiplying each of those numbers by 12. So 0 times 12 is 0. 1 times 12 is 12. 2 times 12 is 24. 36, 48, and 60. And now you're going to add all of those up. So 0 plus 12 plus 24 plus 36 plus 48 plus 60 on your calculator, and you would get 180. That's how you would find the sum. Okay, so now if we're going to do number 2, we're going from 3 to 8. So 3, 4, 5, 6, 7, 8. Those are my inputs. And then my outputs are going to actually be these fractions here. So I'm going to have 3 over, and then 3 plus 1 is 4, so 3/4. Then I'm going to have 4/5, then 5/6, 6/7, 7/8, and 8/9. And now you're going to have to add all those up. I'd highly recommend you use a calculator to add those up. I do have it done already over here on my answer key. So you do get 12,611 over, let's see, 2,520 is what I have on my answer key, if that's correct. So someone can check that for me. I don't have my calculator right here. I don't want to waste a lot of time doing that, but that is what I have on my answer keys, so hopefully that's correct. Okay, so the last thing is formulas for special series. They're kind of just like little shortcuts you can use if you have one of these situations. So the first situation is if you're going from, let's say, 1 to 9 or something, but your rule is simply just that number. If there's no variable for your rule, it's just a number. Then it just says gives the sum of n ones. So if you're going from, like, let's say 1 to 9, and this is just like 9, or it's just that's how many times you're adding up a 1. That's all that means. Or if you have a 1 there. Okay, so if this is whatever number's in for that n, it's just like, oh, okay, that's 9 then. If you had a 19 there, then that would be 19. It's just whatever the number is, because there's nothing to do. So now the next one says gives the sum of positive integers from 1 to n. So if you just have a variable, plain old variable there, right? If I was going to just say go from 1 to 5, right? I would have 1 plus 2 plus 3 plus 4 plus 5. That's how I would do that one. So instead, the shortcut is this little formula here. So, okay, so if I'm going from 1 to 5, that's 5, right? So I would do 5 times 6 divided by 2. 30 divided by 2 is 15. If I added these up, I would have 3 plus 3 is 6 plus 4, and then I get 15 that way too. So you can add them, get all the numbers and add them up individually, or this is a little shortcut you can use when you just have a formula that's just a single variable, and that's it. The last one, when you have just a single variable squared, if you're going from like 1 to 5, you could just do 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, add them up. But what if you were trying to go to like 31? You don't want to sit there and do all of those numbers and add them up. So instead, you take whatever this number is here, this top number, assuming you're going from 1 to that number. Let's say it's 7. Okay? So you would do 7 times 7 plus 1, which is 8, times 2 times 7, 14 plus 1, which is 15. And then you would divide it by 6. And that's how you would get the answer without writing a list of a million numbers. Okay, so using the formulas to solve these. So you notice that the numbers on the top are fairly large. That's why we would use these formulas as opposed to just making the list and adding them. If the numbers are kind of low, making them and adding them is fine. So for this one, all you're going to do is know that the answer is 42. You don't have to do anything because this was a 1. So if you're going from 1 to 42, you're just adding 1 42 times, which obviously is 42. Now for number 2, this time you're going from 1 to 18. So you're basically adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way up to 18, right? So rather than making a list of 18 numbers and then adding them, we can use this little formula here. So it's 18 times 19. So whatever your number is times 1 more. And then you're dividing that by 2. So you're just basically averaging them out. Except you're multiplying them and not adding them. Okay, so that would give you 171. So if you add it up, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, all the way up to 18, then you would just get 171. Okay, then the last one, this time our formula is just a variable squared, and we're going all the way up to 35. That's a lot of numbers to try to figure out and then add together, so we're definitely going to want to use this little formula up here. So you're going to take your n, first of all, which is 35. Then you're going to multiply that by n plus 1, which would be obviously 36. Then you're going to multiply that by 2 times n, so 2 times 35, which is 70, plus 1. And that's going to get divided by 6. That's a lot easier to do in your calculator than adding up 35 numbers after you've squared them. And your answer should be 14,910. All right, so thanks for signing in today to watch. And if you have any questions, please let me know. And obviously, there's a homework alongside this, so get that in as soon as possible. And I will see you tomorrow. Thanks. Have a great day.